Hello, good morning everyone. Today we will see concepts of transient analysis, AC circuit analysis, resonance, AC transients, filter and magnetic circuits, and two-port networks. After completing these topics, we will see some important problems regarding these topics. In transient analysis, we will see about the transient behavior of an inductor and capacitor. Here, first one is inductor. Inductor does not allow sudden change in energy. That is, inductor does not allow sudden change in current. Initial conductor of inductor before 0 and after 0 will remain same. In time domain analysis, we can write inductor current IL of t is equals to IL of initial inductor current plus 1 by L integration of VL of t into dt, where VL of t is equals to L into di by dt. In Laplace domain equations, IL of s is equals to, we will write equation as IL of 0 plus by s plus 1 by SL. Integration is defined as 1 by s VL of s into ds. VL of s is equals to SL into IL of s minus L into IL of 0 plus. Inductor with open circuit is represented by a current source parallel to it, and short circuit at final conditions, inductor is represented as short circuit. When network contains several sources, multiple resistors and inductors, IL of t equation will be changed as IL of infinity plus IL of 0 minus IL of infinity into e power minus t by tau, where tau is equals to L by R equivalent. If inductors and resistors can't be separated, then we should use the Laplace transform. Laplace transform plays an important role in transient analysis. Now we will discuss about the capacitor. Capacitor, we know the basic property, it does not allow sudden change in voltage. Vc of 0 minus is equals to Vc of 0 plus, and voltage across a capacitor at time t can be represented as initial voltage across capacitor plus 1 by C into integration of I of C into dt, where I of C, ICT of dt is equals to C into dVc by dt. Same equations which we represent in the Laplace domain, you can be written as like this as shown. Initial conditions, capacitor is represented by a voltage source, and at final conditions it is represented as open circuit. When network contains several sources, multiple resistors and inductors, the equation can be written as shown here. Time constant is written as R into C equivalent. If capacitors and resistors can't be separated, we should use the Laplace transform, same we have used as in some important points regarding the transient analysis. If the resistance is time dependent, use basic time domain equations instead of Laplace transform or any other shortcuts. So if resistance is dependent upon time, we can use any shortcut without using the Laplace transform. If time dependent source is present in the network transient equations, then the equation is not applicable. Use Laplace transform to solve such problems. If impulse source is present in the network, capacitor or inductor does not follow its property. That means initial inductor current is not equals to initial inductor current after 0. Initial inductor voltage before 0 is not equal to initial inductor voltage, capacitor voltage after 0. See, if impulse source is present, we should use Laplace transform to solve such questions. This type of questions are asked in previous IES exams. If circuit contains multiple unseparable L or C, to determine time constant of circuit, use Laplace transform and obtain function in form of numerator by denominator. To determine the time constant of a circuit, short circuit the voltage source, open circuit the current source, time constant is R equivalent into C equivalent or L equivalent by C equivalent. If dependent source is present, use VI method. Study these important things. Now we can see about the RL source free circuit. In this, resistor and inductor are placed parallel to each other. In the current will enters through the positive terminal of an inductor and leaves through the negative voltage of an inductor. Here current equation can be written as IL is equals to current entering into the inductor is I0 e power minus t by tau. This represents the current is decaying exponentially in an inductor. Voltage is negative of I0 into R into e power minus t by tau. So VL of t is minus I0 into R into e power minus tau. This is decaying negative in negative term. This is RL source free circuit. Next we'll go for the RL source circuit, which is exactly opposite. It consists of RL circuit with a source. In this, current is written as Vs by R into 1 minus e power minus t by tau. In this, current rises gradually and reaches to the final value. So the equation you will get it as Vs by R into 1 minus e power minus t by tau. Here VL of t, it decreases gradually positive from positive maximum voltage Vs into e power minus t by tau. So this is the RL source circuit. Now we'll talk regarding RC source free circuit. In this circuit, it consists of a resistor and capacitor which are free from source, which does not have any source. In this also, voltage across a capacitor decreases exponentially and current across a capacitor also decreases exponentially in negative term. I will say some tips how to solve such types of question, different types of question. First one, while calculating I, di by dt, d square I by dt square at t is equals to 0. First step, first you have to find IL of 0 or initial inductor current or initial capacitor voltage. Now, write differential equations for time period greater than 0. At each step, find desired value and differentiate differential equation. Here IL of 0 minus is equals to IL of 0 plus is equals to 0. Here initial conductor across an inductor before 0 and after 0 is 0 because the switch is get open. Here voltage equation can be written as V is equals to IR plus L into DIL by dt. You will get equation as DL by dt is equals to V minus IL into R by L. If you differentiate again this term, you will get d square IL by dt square is equals to minus R by L into di1 by dt. Here d square IL by dt square of 0 plus is equals to minus R. Here di by dt is replaced by V by L, so RV by L square. Same thing happens with a resistor and capacitor having the voltage source. Initial voltage across a capacitor before 0 and after 0 remains 0 because the switch is open. IC will be V minus VC by R, where IC of 0 plus is equals to V minus VC of 0 plus by R. IC of 0 plus is equals to VC of 0 plus is 0, so replace it by 0, you will get V by R. Differentiate it and again you differentiate second time, you will get the equation as V by R square C square. Now we will see the basic terminology regarding AC circuit analysis. First term is form factor. Form factor is equals to RMS value by average value. Remember it as fraction, FRA. Form factor, R means RMS value, A means average value. Peak factor or crest factor, remember it as CMR. crest factors or peak factor. C is equals to M maximum value by RMS value. Note, if f of t is equals to dc term plus a1 sin omega t plus a2 sin 2 omega t, average value is a0, RMS value can be written as shown here. If source contain multiple frequencies, superposition theorem is used. Superposition theorem can't be used for power of calculations, it cannot be used for transformers also. Here we will see now a different excitation analysis. Here excitation is DC, which is a constant value. Average value will get as maximum value and RMS value also will get as a maximum value. Remember, for a constant DC value, both average and RMS values are same. This is the basic sine wave which we will use in electrical engineering. Here sine wave, the positive has positive maximum value Vm, negative has negative maximum value Vm. For sine wave, average value is 0 for full cycle and average value for half cycle is 2 Vm by pi and RMS value is Vm by root 2. This is the half wave rectifier sine wave. In this, the waveform will be from 0 to pi, and from pi to 2 pi it will be 0, and from 2 pi to pi it will be 2 pi to 3 pi, it will give maximum value. For this, average value is Vm by pi, RMS value is Vm by 2. This is also known as half wave rectifier sine wave. For full wave rectifier sine wave, there will be no gap between pi and 2 pi. Continuously it will conduct to a maximum value. Here average value is 2 Vm by pi, which is equal to average value of half cycle of sine wave, and RMS value is Vm by root 2. So for sine wave and full wave rectifier sine wave, for half cycle, average value and RMS value both are same. For symmetrical square wave, this value and this value will cancel out each other. So average value will be 0 for half cycle and average value is plus or minus Vm for half cycle. RMS value is equals to Vm, which is same as DC excitation. This is the square wave which is not symmetrical, means up to t by 2 it will be conducting, and from t by 2 to t it will be 0, from t to 3t by 2 it will be conducting. In this, average value is Vm by 2, RMS value is Vm by root 2. Symmetrical square triangular wave, in this average value is Vm by 2, RMS value is Vm by root 3. So remember, for symmetrical triangular wave, RMS value is Vm by root 3, average value is Vm by 2 for half cycle. Then unsymmetrical triangular wave, in this average value is Vm by 2, same as RMS value is Vm by root 3. So for both symmetrical and unsymmetrical triangular wave, average value is Vm by 2, RMS value is Vm by root 3. Note, for symmetrical waveforms, whether it will be a square wave, sine wave or triangular wave, RMS value of half cycle is equals to RMS value of full cycle. Now we will see about the series circuit. This is the RL series circuit which is energized by the voltage source. Here voltage can be written as under root VR square plus VL square. Z is equals to under root of R square plus XL square or omega L square. Phase angle will be tan inverse of XL by R. Here for inductor, current lags voltage by an angle phi. Cos phi is R by Z, or voltage across a resistor by source voltage, which is known as a power factor. Similarly, for RC series circuit, it consists of a resistor and capacitor in series with a voltage source. V is equals to under root of VR square plus VC square. Z is equals to under root of R square plus XC square. XC is equals to 1 by omega C whole square. Phase angle is equals to tan inverse of 1 by omega RC. Here current leads voltage by an angle of phi. Cos phi is equals to VR by V or R by Z, same as in RL circuit. we will see the combination of RLC circuit, resistor, inductor and capacitor. Three components, electrical components are connected in series with the voltage source. Here XL is equals to omega, X is equals to 1 by omega c. V is equals to under root VR square plus VL minus VC whole square. Z is equals to R square plus XL minus XC whole square. Phi is equals to tan inverse of XL minus XC by R. If XL is greater than XC, current lags voltage by phi. If XL is less than XC, current leads voltage by phi. If XL is equals to XC, current is in phase with V, which is at resonance. Same as its cos factor is cos phi, which is a power factor, with cos phi is equals to R by Z or VR by V, voltage across a resistor by source voltage. Now we will see about the parallel RL circuit. Resistor and inductor are kept in parallel with the current source. Voltage will be same for the parallel circuit. Here I is equals to IR under root of IR square plus IL square. Here impedance is replaced by admittance in parallel circuit. So admittance is equals to reciprocal of resistance whole square plus reciprocal of XL whole square. Phase angle will be opposite to the series circuit. Phi is equals to tan inverse of R by omega. Here current lags voltage by phi, where cos phi is equals to IR, current across the resistor by source current. RC parallel circuit. If resistor and capacitor are connected in parallel with the current source, I is equals to under root of IR square plus IC square. Similarly, Y admittance is equals to reciprocal of resistance plus reciprocal of XC. XC is equals to 1 by omega C. So reciprocal of 1 by omega C is omega C whole square. Phi is equals to tan inverse of omega RC, where I leads V by phi. Power factor is equals to IR by I. Combination of a RLC parallel circuit, same equations, IL minus IC, XL minus XC whole square. Phi is equals to tan inverse of imaginary part by real part. Here in series circuit, if XL is replaced by BL, XC is replaced by BC. If BL is greater than BC, I lags V by phi. If BL is less than BC, I leads V by phi. If BL is equals to BC, I is in phase with V. Cos phi is IR by I, where BL is 1 by omega L, BC is equals to omega C, opposite of reactance. Now we will see the response analysis of second order circuit. First we will consider about the RLC series circuit. Characteristic equation can be written as S square plus R by LS plus 1 by LC. Also this can be written as S square 1 by tau S plus 1 by LC, where tau is equals to L by R. If 1 by tau L by R, if R goes to the up, it will goes to the numerator, R by LS into C plus 1 by LS while C is equals to 0. Damping factor, this term is represented by an alpha. It can be written as 1 by 2 tau, where tau is equals to L by R, where R goes to the numerator, you will get as R by 12. So remember every time damping factor is represented by alpha, and it can be remembered as 1 by 2 tau. Time constant, it is inverse of damping factor. If you will get damping factor, you will get time constant. So this is the natural frequency formula 1 by root LC, which is a standard one. Coming to the RLC parallel circuit, in this characteristic equation is S square 1 by tau. Tau represents RC for RLC parallel circuit. S square plus 1 by RCS plus 1 by LC is equals to 0. In this damping factor 1 by 2 tau, 2 RC. Time constant is inverse 1 by damping factor. Natural frequency is same as series RLC circuit, that is 1 by root LC. Now we will see about the AC power concept. Apparent power, S is equals to Vrms into Irms conjugate. Remember here RMS terms are used. RMS RMS conjugate. Active power is equals to Vrms Irms cos phi. Reactive power is equals to Vrms Irms sin phi. Here instantaneous power which will oscillate at 2 times the frequency, it is written by the equation Vm Im by 2 into cos of angle voltage angle minus current angle cos of 2 omega t plus theta v plus theta I. Keep in mind that instantaneous power oscillates at 2 times the supply frequency in AC circuits. Double times the supply frequency in AC circuits. This was asked in the competitive exam. Note, in AC circuit, net energy stored by the inductor and capacitor is 0. Hence, average power consumed by the inductor or capacitor is 0. So, inductor does not consume any power, and also the capacitor also does not consume any power. This is one of the important formula. These two powers are P1 and P2. These are the powers consumed under voltage source V1 and voltage source V2. The power consumed in the resistor when these both sources are working simultaneously, then you will get as P is equals to individual power root whole square. Individual power P1 plus or minus individual power P2 whole square. Don't take whole P1 plus P2 whole square. This is the common mistakes where all will make. Individual power plus individual power P2 whole square. Resonance concept. Resonance means oscillation of energy between two forms, that is one electrostatic form and another is one electromagnetic form. At resonance, power factor is 1, current is in phase with voltage, imaginary part of Z is 0 and imaginary part of admittance is 0. It consists of only real part. Quality factor determines sharpness of resonance curve. Quality factor determines sharpness of a resonance curve. See, in RLC series circuit, omega resonant frequency is represented by omega naught, that is 1 by root LC. Quality factor for series RLC circuit is Q is equals to omega naught L by R or 1 by omega naught RC. If you replace omega naught by root LC, you will get the term 1 by R into root LC, or quality factor can be written as omega naught by bandwidth. Bandwidth is nothing but the higher frequency component minus lower frequency component. In series RLC circuit, this is the resonant frequency, and below the resonant frequency XL is less than XC, and above the resonant frequency XL is greater than XC. Here it will be lagging and before that it will be leading. This is the graph of current versus frequency. Here at point 0 everything is 0, and at lower frequency current becomes Im by root 3. At a resonant frequency current will be Im, and at a higher frequency current will be Im by root 2. Later gradually it decreases to 0. Means at lower frequency and higher frequency maximum current will be Im by root 2. At resonant frequency maximum current will be Im. Where WH, here WL is represents the lower half power frequency, WH represents the upper half power frequency. These WL, W0, WH, these three all are always in geometric progression. This will omega naught is equals to geometric progression of omega H and omega L. Bandwidth, already I have mentioned that it is the difference between the higher frequency minus lower frequency, which can be written as R by L. This RLC series circuit can also be treated as current acceptor circuit or voltage amplification circuit. In series RLC circuit, you will have lowest impedance, the Z is equals to R, and it is also known as a band pass filter. In case if bandwidth, which is the difference between the higher frequency minus lower frequency, which is less than omega naught, then higher frequency formula can be written as omega naught plus bandwidth by 2. Lower frequency can be written as omega naught minus bandwidth by 2. This formula is applicable when if and only if bandwidth, that is higher frequency minus lower frequency, is less than resonant frequency. RLC parallel circuit, it is also known as a band rejector filter. It has minimum admittance. Parallel RLC circuit has minimum admittance and maximum impedance. It is also known as a current rejector circuit, whereas series RLC circuit is called as a current acceptor circuit. Resonant frequency will be same as a series circuit. Omega naught is 1 by root RLC. Q is equals to omega naught into RC or R by omega naught L. If you replace omega naught by 1 by root LC, you will get this formula. Same as series RLC circuit, Q is equals to omega naught by bandwidth. Bandwidth represents a higher frequency minus lower frequency component. It is also a geometric progression. Omega naught is equals to under root of omega h into omega L. In series RLC circuit, bandwidth omega h minus omega L is equals to R by L. In parallel RLC circuit, bandwidth is equals to 1 by tau 1 by RC. Bandwidth is equals to 1 by eta square, some miscellaneous formulas. Alpha is equals to bandwidth by 2, where alpha is the damping factor. Time constant is equals to 1 by alpha. At resonance, admittance is minimum, hence current is minimum, so parallel resonance is anti-resonance. Admittance is minimum means impedance is maximum. If impedance is maximum, it is also known as current rejector circuit. So series RLC circuit is known as current acceptor circuit and it is in resonance condition. Parallel RLC circuit is known as current rejector, it is known as anti-resonance circuit. This is one of the important parallel circuit which is asked in the competitive exam. This is also known as a tank circuit. In this, the resistor and inductor will be in one branch and capacitor will be in another branch. Here you will get formula as omega naught is equals to and whole under root 1 by LC minus R by L whole square. This is the resonant frequency formula. Keep in mind omega naught is equals to under root 1 by LC minus R by L whole square. At resonance, impedance of a circuit is given as L by RC. This you have to remember. For ideal tank circuit, resistance is 0, then impedance will be infinite. RL and RC parallel circuit. If RL and L and RC and C are in parallel, resonant frequency formula is, first you have to write omega naught is 1 by root LC under root RL square minus L by C, RC square minus L by C. Please keep in mind. Quality factor, which is directly proportional to the sharpness at resonance, it can be also represented as 2 pi into maximum stored by inductor or capacitor by energy dissipated per cycle. For RL circuit, for series, omega L by R or VL by VR, 1 by omega CR, VC by VR. Please keep these formulas in mind. Note point is selectivity is inversely proportional to bandwidth. At half power frequency, power dissipated in the parallel resonance circuit will be half of the power. Now, we will see the basic concept of AC transients. In this, the source voltage is Vm sin omega t plus phi. Here you will have a switch which is closed at t is equals to t naught. This is a resistor and inductor. Listen carefully, this concept will come in the transients in transmission line in power system. Here, by seeing resistor and inductor, you can write down the impedance under root of R square plus omega L whole square. Impedance angle is tan inverse of imaginary part by real part, omega L bar. Time constant is R by L. So by seeing R and L, you will write impedance, impedance angle and time constant. Now look at the current through the inductor IL of t. First he took DC offset current which is decaying exponentially. Then he took Vm by impedance sine of omega t plus phi, which is the source voltage, he is subtracting this omega t plus phi. He is subtracting theta z impedance angle. This impedance angle he is subtracting from the source voltage. This is the steady state volt current. This is the DC offset current. When the switch is closed at t is equals to t0, initial inductor does not allow sudden change in current. Initially inductor current is 0. At t is equals to t0 plus also inductor current is 0. Substituting this inductor current in the previous equation, you will get this equation. If this Vm by Z goes to the left hand side, this becomes negative and this becomes positive. So he has written as A is equals to Vm by Z into sine of theta Z minus phi minus omega naught. Now we need any circuit need transient free response. So for such condition, to get transient free response, there are some conditions. RL series and parallel circuit. Here source voltage is same as Vm sine omega t plus phi. Sine term he is using. Here omega t plus phi, this bracket part omega t plus phi, which is equals to the impedance angle for tan inverse of omega L by R. In case if voltage is Vm cos omega t plus phi, here cos term is using, you will get sine term, you will get cos term from sine term by adding 90 degrees. So omega t plus phi is equals to 90 degrees plus theta z, that is equals to tan inverse of omega L by R. If source voltage changes to cos, sine to cos plus 90, you will add plus 90 to the impedance angle. Now RC series and RC parallel circuit, same as here source is sine omega t plus phi, you will get omega t plus phi is equals to tan inverse of omega RC. If the source voltage is replaced by cos term, you will add plus 90 degrees. Transient free response, it is an imaginary thing. It is not possible at all in each and every network which consists of resistors, inductors and capacitors. If there are storage elements in a network, then you will get somewhat transient in that network. There will be no transients only if stored networks are absent. Worst if transient response is worst by having the storage elements, condition to that worst transient response is for RL circuit and parallel RC circuit, same as source voltage is Vm sine omega t plus phi. Here omega t plus phi, now it is replaced by opposite to the transient free response, 90 degrees plus theta z. If it is cos, it is replaced by theta z. Same for the RC and RC parallel circuit, series and parallel circuit. Sin omega t, 90 degrees is added. If it is cos omega t, 90 degrees is not added. Now we will see the basic concept of passive filters. Filters are designed using the passive components. Passive components are resistor, inductor and capacitor. To check what type of filter it is used, check at omega is equals to 0 and omega is equals to infinity. At omega is equals to 0, at 0 frequency, inductor is short circuited, capacitor is open circuited. At infinite frequency, inductor is open circuited, capacitor is short circuited. Now I will say how to find out the type of passive filters. If it is a high pass filter, at omega is equals to 0, you will get low value. At omega is equals to infinity, you will get high value. At infinity condition, at omega is equals to infinity, you will get high value, means it is high pass filter. Low pass filter is opposite to the high pass filter. At omega is equals to 0, you will get high value. At omega is equals to infinity, you will get low value. Band pass filter, at both the frequencies, at omega is equals to 0 and omega is equals to infinite, you will get low value. band reject filter, or it also called as all pass filter. At omega is equals to 0 and omega is equals to infinity, you will get high values. To differentiate the band reject and all pass filter, check response at any intermediate frequency. Take magnitude of that frequencies. If that is constant, then it is determined as all. Now we will see about the magnetic circuits. Series magnetic circuit. Here source voltage is connected to this transformer, and you have a small gap. Due to this small gap, the magnetization current will increase and it will merge this equipment. Reluctance is offered by the magnetic circuit is reluctance offered due to this iron part and reluctance offered due to this air gap. Reluctance formula is L by mu A, or we can say that flux is equals to mmf by reluctance, which is a basic formula. Inductance can be related to reluctance by L is equals to n square by S. Stored energy in an inductor is half Li square. Force is negative of differentiation of energy with respect to x. Self-inductance. EMF produced in itself due to current flowing in its own winding. L is equals to mu n square A divided by L. That is known as self-inductance. Mutual inductance. EMF produced in one winding due to the current flowing in the another winding due to flux linkage of other winding. Mutual inductance. N1 into 512 by I2, N2 into 521 by I1. If number of turns in primary winding, you will get in denominator as secondary current. If number of turns in secondary winding, you will get current of primary winding in denominator. Keep this in mind. If here it is 1, 512, if here it is 2, here 521. Now coefficient of coupling. It is represented by K. K is equals to M by root L1 L2. If K is equals to 1, this determines the windings are tightly coupled. If K is less than 1, moderately coupled. If K is equals to 0, loosely coupled. See in this diagram, windings 1, 2 and 4 have same voltage polarity, as flux produced due to current flowing in this winding have same direction. Now I will tell you how to calculate the KVL in the magnetic circuit. Here source voltage, you have resistor, inductor, you have dot convention, opposite, and you have one capacitor. First equation, write in the first loop, V is equals to R plus J omega L1 into I1 plus J omega M into I2. Here J omega L2, write the equation in second loop, J omega L2 minus J by omega C into I whole I2 plus J omega M into I1. Similarly, write in this loop, V is equals to R plus J omega L1 into I1 minus J omega M into I, J omega L2 into I2 minus J omega M into I1. Here stored energy in the coupled circuit can be represented as half L1 I1 square, half L2 I2 square plus M times plus or minus M times I1 I2. Plus denotes for adding polarity, minus denotes for opposing polarity. I1 and I2 are steady state currents. Here magnetic aiding, when current enters through two dots, represent this circuit by this as T, represent this as T circuit. This part is represented by M, and now subtract M from L1 and now subtract M from L2. Series aiding circuit. If current is entering into the both terminals, L equivalent can be represented as L1 plus L2 plus 2M. Energy is I square into L plus M. In series opposing, current is entering one through dot and leaving through the dot. You can represent L equivalent as L1 plus L2 minus 2M. Parallel adding, if both dots are at same point, same polarities, L equivalent is L1 L2 minus M square by L1 plus L2 minus 2M. Parallelly opposing means both dots are at different points, L1 L2 minus M square by L1 plus L2 plus 2M. Now we will see about the new topic, two-port networks. Basic information is number of parameters of the network can be calculated by using the formula NC2, which we will use in the probability. Z parameter equations are V1 is equals to Z11 I1 plus Z12 I2, Z21 I1 plus Z22 I2. For condition for symmetry is Z11 diagonal elements must be same, Z11 is equals to Z22. Condition for reciprocity of diagonal elements must be same, Z12 is equals to Z2n. For series elements, Z parameters can't be defined. Z parameters cannot be defined or described for series elements. Keep this in mind. Z parameters also cannot be defined for ideal transformer. Now shunt element. If there is a Z in middle, you can represent the total as Z, 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 Z. If it is represented in the T network, first add this to Z1 plus Z2, Z2, Z2 and Z2 plus Z3. Add in the diagonal terms, off diagonal terms keep same as Z2 and add the next diagonal term Z2 plus Z3. Here this is the series connections of the network. This is the two-port network and this is the network 1 and this is the network 2. You have applied the voltage source V1 and voltage source V2, and this voltage source is delivering current I1 to this network. This voltage source is delivering I2 to this network. This voltage source, this I1 will be transferred. This will form a closed circuit by travel. I1 current will form a closed circuit by traveling like this, and it will flows like this, and like this it will flows, and it will reaches to the negative terminal. Similarly, this I2 will flows like this, like this, like this, and it will reaches to the negative terminal. In series network, both Z parameters are added. Now we can see about the Y parameters. I1 is equals to Y11 V1 plus Y12 V2. I2 is equals to Y21 V1 plus Y22 V2. Please remember these equations. For condition for symmetry, diagonal elements must be equal, off diagonal elements must be equal. For reciprocity, same as for Y, same as Z parameters, Y parameters, shunt elements cannot be defined. Keep in mind, series elements cannot be defined for Z parameters cannot be defined for series element, Y parameters cannot be defined for shunt element. Here series element, this is in series, so you can represent of inverse of Z 1 by Z and negative minus 1 by Z, minus 1 by Z and 1 by Z. This is the pi network. Add these two terms and take negative of the minus Y2, you will get this matrix. This is the parallel connection of a network. Here voltage source V1 and voltage source V2 is applied. Current I1 enters, and this connection is the parallel combination of a network. Please observe. Now we will see about the ABCD parameters. Equation of V1 is equals to AV2 minus VI2, I1 is equals to CV2 minus DI2. Condition for symmetry is obviously A is equals to D, and condition for reciprocity is AD minus BC equals to 1. Series element for ABCD is 1Z01, shunt element 101 by Z1. For cascade of connections, we use T network. We multiply the two T networks. See here, this is the network 1 and network 2. That cascading will be represented by the T network. H parameters, here V1 is equals to H11 I1 plus H12 V2. I2 is equals to H21 V1 plus H22 V2. Please remember these equations. Condition for symmetry is determinant Determinant must be equals to 1. A determinant is equals to h11 h22 minus h21 h12 is equals to 1. Condition for symmetry is equals to h12 is equals to minus h21. In series parallel connection, keep this in mind. In series parallel connection, h parameters are added. This is the interconnection of a network. These two are added. Okay, keep this in mind. This is an important one. In series parallel connection, h parameters are added. Now we will see about the g parameters. I1 is equals to g11 v1 plus g12 I2. V2 is equals to g21 v1 plus g22 v2. Same as for h parameters. G parameters or first condition for symmetry is 1. Condition for reciprocity is g12 is minus g21. In h parameter, in series parallel connection, h parameters are added. In parallel series connection, g parameters are added. GPS, remember as GPS, G parameters, parallel series. Now we will see some important relations. Y is equals to Z inverse, G is equals to H inverse, A dash, B dash, C dash, D dash is equals to A, B, C, D whole inverse. Two-port network for ideal transformer. For ideal transformer, Z and pi parameters can't be defined. ABCD parameters can be defined such as N is one diagonal, 1 by N is another diagonal, and other two off diagonals are 0, where N is turns ratio, N1 by N2. Remember, turns ratio and transformer ratio is two different terms. Turns ratio is N1 by N2, transformer ratio is N2 by N1. H parameter is defined as for ideal transformer. Both diagonal elements are 0 and off diagonal elements are negative to each other, N and minus N. This represents the lattice circuit. Condition for symmetry is Z1 is equals to Z2. Condition for reciprocity Z3 is equals to Z4. Z parameter of lattice network when these two are same, ZA is ZA, ZB ZB. Z parameters is ZA plus ZB by 2. Off diagonal elements are ZA plus ZB by 2. Off diagonal elements are ZA minus ZB by 2. Now we will see the new topic, graph theory, which is a small topic. Basic concepts. Twigs. What do you mean by twigs? It is represented by a solid line, strong line or dark line, something. It is represented by solid line. Number of twigs in the graph is n minus 1, where n represents the number of floats. Links. It is represented by the dotted line, weak line. Number of links in a graph is b minus n plus 1. Rank of a graph. You can find what is the rank of a graph by using the n minus 1 formula. It is the number of independent equations. Branches, probability formula NC2. NC2 is n into n plus 1 by 2. Number of branches in the network is n into n plus 1 by 2. Tree. A tree of a graph contains all nodes of a graph formed by twigs, that is n minus 1 branches. Does not have any closed part, and it is not unique. Tree is not unique. It is different. Tree is different. Keep in mind, not unique means different. Tree is different. Number of trees for a complete graph is represented by formula n power n minus 2. For closed path to exist, branches must be greater than or equal to nodes. Incidence matrix. Order of a matrix is nodes into branches. It has some properties. If branch direction at node 1 is entering, take minus 1. If it is leaving that node, take plus 1. Sum of all elements in any column of a matrix is 0. If two graphs have same impedance matrix, they are known as isomorphic graphs. Identical, same incidence matrix. Reduced incidence matrix Incident matrix order is nodes by branches. Reduced incidence matrix is nodes are reduced by 1 into branches obtained by removing last row from the incident matrix. Now we will see about the cut set matrix. Group of branches containing only one twig and rest all are links, means only one solid line, rest all are dotted lines. They are called as cut set matrix. Cut set branches must divide the graph into two parts. Number of the fundamental cut sets are n minus 1 also is equal to number of KCL equations, number of twigs or number of node pair voltages. So n minus 1 is the formula for number of fundamental cut sets, number of KCL equations, number of twigs, number of node pair voltages. Order of a matrix is n minus 1 into B, which is same as reduced incidence matrix. Properties, please study here. Now we'll see about the tie-set matrix. Group of branches containing only one link and rest all are twigs which are solid line. It is opposite to the cut set matrix. Number of fundamental tie sets is B minus n plus 1, which is equals to number of links, it is equals to number of KVL equations. Order of a matrix is given as B minus n plus 1 by B. By this we have completed the revision of network analysis. Today onwards we will see some important problems regarding network analysis and solve the problems. Now we will see some problems regarding the network analysis. In this question, the switch is initially closed and switch 2 is open. The inductor carries an current of 10 amperes and capacitor is initially charged to voltage of 10 volts, and polarities of the switch is closed at t is equals to 0 and switch 1 is opened at t is equals to 0. He is asking to find the current through capacitor and voltage across the inductor. Here at t is equals to 0, initial inductor current is 10 amperes and capacitor initial voltage is 10 volts. So at t is equals to 0, switch 1 inductor acts as an open circuit and capacitor acts as a short circuit. At t is equals to 0, inductor acts as a current source and capacitor acts as a voltage source. You will get the circuit as this inductor acts as a current source and capacitor acts as a voltage source, and here you have to apply the voltage nodal analysis. 10 amperes is equals to V by 10, V minus 10 by 10, so you will get V as 55 volts. He is asking to find the current through the capacitor, but current flowing direction is this. Current is equals to V minus 10 by 10, 55 minus 10 by 10 is equals to 4.5 ampere. In this question, he is asking to find the value of current I and rate of change of inductor current at t is equals to 0. Here we have a parallel RLC circuit with a switch open. He is saying that the switch is open for long time. Initial conditions, as the switch is open from long time, this will become redundant and I of 0 minus will be equal, switch is opened, will be 0. At 0 the switch is closed, voltage across a resistor will become minus 50 volts, so current will be minus 5 amperes. And at t is equals to 0 plus, as switch is closed, voltage across the resistor, inductor and capacitor is same, that is 50 volts. We know L into DIL by dt is equals to 50 volts. Here L value is 0.1, so 50 by 0.1 is equals to 500 amperes per second. In this question, he is asking the impulse response under the condition of R1 C1 is equals to R2 C2. Here we have done the voltage division rule. V2 of S by V1 of S is equals to R2 parallel with 1 by SC2 by total R1 parallel with 1 by SC1 plus R2 parallel with 1 by SC2. Here V1 of S is equals to 1 because impulse response means applied voltage is impulse signal. V2 of S you will get by calculating those values R2 by R1 plus R2, where C2, this denominator will get cancelled because C2 R2 is equals to C1 R1. So from this question, option B is the right answer. In this question, he is asking to find the time constant of the given circuit. The given circuit consists of two parallel capacitors in series with one capacitor, one resistor, one 3 ohm resistor and 3 ampere current source. Now to find time constant, open this current source. So C equivalent will be 1 plus 1, 2 parallel 1, 2 series 1. So 2 into 1 by 2 plus 1, 2 by 3. R equivalent will become 6 ohms. Tau is equals to R into C, where R equivalent is 6 ohms, C equivalent is 2 by 3. You will get answer as 4 seconds. In this circuit, it consists of capacitor, resistor, one switch, a resistor in parallel with RC. He is asking to find out the value of I0 plus. Initially, the switch is open and capacitor is uncharged, C2 is uncharged. Voltage across the capacitor C2 is 0. At t is equals to 0 plus, capacitor is short, you will get R equivalent as 2 plus 2 parallel with 1. You will get 8 by 3. I of 0 plus, source current Is of 0 plus is equals to V by R, where V is 4 by R equivalent is 8 by 3. You will get as 1.5. Now we have to find current in this branch. I of 0 plus is equals to 1.5 into opposite resistance by total resistance. In this total problem, first he had found R equivalent, then he have found the source current by using R equivalent. After that he have find out the current in the 2 ohms branch. A square pulse of 3 volt amplitude is applied to the CR circuit as shown in the figure. This is the pulse voltage and this is the circuit. The capacitor is initially uncharged. The output voltage at time t is equals to 2 seconds. First of all, it has 2 capacitors and 1 resistor. Initial voltage is 3 volts. Output voltage is not. He is asking to find the output voltage at t is equals to 0. T is equals to 2 seconds. Initially output voltage is 0, open circuit. So this capacitor is useless. No current flows through this capacitor. When we connect 3 volt source, we see initial conditions it acts as a short circuit. At final conditions, capacitor acts as open circuit, and this source voltage 3 volts is came across capacitor. We know the formula of time constant. RC is equals to 0.1 milliseconds. This is with source, so equation will be 3 into 1 minus e power minus t by tau. At t is equals to 2 seconds, Vc you will get it as 3 volts. it is at t is equals to 2 plus just after 2, Vs is 0 volts, Vc is 3 volts, so output voltage is 0 minus 3 volts. You will get it as minus 3 volts. See, in this circuit it is a RC circuit with switch open. Initial current across the inductor is 0 and initial capacitor voltage is 50 volts. Polarities is as shown figure. Switch S is closed at t is equals to 0. Find inductor current. First of all, we have found omega naught is equals to 1 by root LC, and it is a source free circuit. I is equals to V naught into root C by L into sin omega naught t. Phi into root C by L. You will get it as sin 1000 t. And series RLC circuit has resistance and current which lags behind the applied voltage by 45 degrees. If the voltage across the inductor is twice the voltage across a capacitor, what is the value of inductive reactance? He is saying that current lags voltage by 90 degrees. So impedance angle will be 45. VL is 2 times VC. VL is nothing but I into XL. So XL is 2 times XC. Here theta is equals to tan inverse of XL minus XC by R, because L dominates 45 degrees. By if tan inverse goes to the right hand side, it will become XL minus XC by R is equals to 1. Here XL minus XC is equals to R. Here already given that XL is 2 times XC. So XC is equals to R. XL is equals to 2 times R, where R value is 20 ohms. So 2 times 20 is 40 ohms. In this circuit, the power consumed by the 5 ohm resistor is the 10 watts. Then he is asking the power factor of the circuit. By resistor, power consumed is 10 watts, means IRMS square into 5 is equals to 10. You will get the IRMS value. Maximum value, RMS value is maximum value divided by root 2. So maximum value you will get it as 2 amperes. Impedance you can write as maximum voltage by maximum current. You will get it as 25 ohms. Here tan inverse theta is equals to tan inverse of XL by R, with theta is equals to tan inverse of XL you have to find out, and R value is 10 plus 5, 15 ohms. Here Z is equals to 25 is equals to under root of R square plus XL square. You will get XL value as 20 ohms. Power factor cos theta is equals to, you will get it as 0.69. Here if the power consumed by the resistor, you will take current as RMS value. You will get RMS value. You will find the maximum value. This maximum value will be same in the series circuit. From that you will find the impedance. From that impedance you will find XL. From that you will find theta, and power factor is cos theta. In the series RLC circuit, the partial phasor diagram at certain frequency is shown, the operating frequency. In this phasor diagram, this is voltage V, this is current I, and this is voltage across a capacitor. Current, this is the voltage across resistance. Here voltage across a resistance and current are in same phase. Here I leads V. If current leads voltage, then capacitor dominates, that is XC is greater than XL. 1 by omega C is greater than omega L. omega is less than 1 by root LC. So the operating frequency will be less than the resonant frequency. This is the LC circuit without any source. In this question, the initial current is given as 5 amperes. The initial voltage across a capacitor is given as 10 volts. He has given the inductor value and he has given the capacitor value. He is asking the voltage across a capacitor after t greater than 0, at t is equals to 0 plus. See, when there is an initial voltage given without any source, you will use initial voltage into cos omega t. If with source, you will use initial voltage into 1 minus sin omega t. See, here he has given the initial voltage as 10 volts. Voltage across a capacitor will be 10 cos omega t. As t increases, cos omega naught t decreases. Means capacitor voltage will get discharged current without source, so it is 5 cos omega t. Voltage with this inductor current, you will find the capacitor voltage 5 into root L by C into sin omega naught t. Now you will add this first equation and second equation. Voltage across a capacitor is equals to 10 cos omega naught t plus 5 into root L by C into sin omega naught t. You will substitute those values where omega naught is 1 by root LC. When you substitute those values, you will get answer like this. So with the initial voltage across a capacitor, you will find the voltage across a capacitor. With initial current across the inductor also, you will find the voltage across a capacitor. The main aim of initial voltage across an inductor and initial current across inductor and initial voltage across a capacitor is to find the voltage across a capacitor and add those two values. This is one important diagram in electrical engineering. If the numbers serially rotates in anti-clockwise direction 3, 4, 5, directly you should write phi 1 is equals to 53.14 and cos phi is 0.6. If these numbers rotate serially in clockwise, you should write phi 2 as 36.86, cos phi is 0.8. These are some important formulas regarding network analysis. If apparent power is equals to under root of P square plus Q square, where P is the real power, active power, Q is the reactive power. Q is equals to 0 for resistive load. If reactive power is less than 0 for capacitive load, leading power factor. Reactive power is greater than 0 for inductive load, lagging power factor. For leading power factor, if reactive power is less than 0, capacitor delivers reactive power, inductor absorbs reactive power. In this question, he is asking to find the average power supplied by the source. If average power is supplied for the source, it will be observed only by resistance. Here he have done nodal analysis, V by J2, V by 2. He have got P value. Simply he have used the formula P is equals to V square by R value 200 watt. So from this problem we can conclude that average power is observed only by resistor. This problem comes under the topic of superposition theorem. Here voltage source is given with fundamental frequency and secondary frequency. He is asking the average power dissipated by 1 ohm resistor. By using superposition theorem, we will take the fundamental frequency 10 at an, this is the maximum value, RMS value is maximum value divided by root 2. So here he had took RMS value, this is the RMS value 1, and he had converted XL is equals to omega j omega L, where j is present here, omega is 1 and L is 1. From this he have calculated the current 10 at an angle of 0 by 10 at an angle of 20 by 1 plus j, which you will get as 10 by root 2 at an angle of minus 25 degrees. Next he took the secondary frequency value, where RMS value is maximum value by root 2, 1 ohm, and omega is 2, so J2. He had find out the current, you will get it as 5 root 2 at an angle of minus 43.3. He is asking to find the average power. Average power dissipated by resistor is IRMS square into R. Now we have to find the IRMS square, that is under root of first current RMS whole square plus second current RMS whole square. First current RMS value is 5 root 2. Second current RMS value of magnitude is 5 root 2. You will get 10 amperes. P is equals to IRMS square into R. 100 into 1 ohm is equals to 100 watts. In this question, two circuits have same magnitude of impedance. They are connected in parallel. Power factor of one impedance is 0.8 and power factor of other impedance is 0.5. This parallel combination power factor, overall power factor he is asking. There is one direct formula to find the power factor of parallel circuits, that is 1 by under root of 1 plus A plus B whole square. You can remember it as A plus B whole square. 1, which is constant, plus A plus B whole square, that is cos phi 1 plus cos phi. No, A square plus B square whole square. Remember it as 1 by A square plus B square. You will square inside and add them, and you will do overall square. You will get answer as 0.0707. In this he is asking to find the RMS current I of t. Here omega is 1. XL is equals to omega L, which you will get as 1 ohm. XC is equals to 1 by omega C, which you will get as 1 ohm. These both inductor and capacitor are series. When they have equal values, they will get short circuited. When they get short circuited, you will get the circuit like this. When inductor and capacitor are in series, they will get short circuited if they have same values. You will get one resistor value, and this 1 ohm resistor will be short circuited. Overall you will get RMS value I is equals to IRMS is equals to VRMS by 1, that is 1 by root. In this problem you have to keep in mind that when inductor and capacitor having the same value are connected in series, then both will get short circuited. Here you can see Q factors of a different element. For solo resistance, Q factor is 0. For single inductor, Q factor is infinity. For single capacitor, Q factor is infinity. For resistor in series with inductor, omega L by R, 1 by omega RC. This is 1 by R into root L by C. A series RLC circuit is excited by a AC voltage source. Quality factor is given. He is asking the amplitude of current in ampere at upper half power frequency will be. Here series RLC circuit. Quality factor we can write it as 1 by R into root L by C. From this the L and C values are given. You will get the R value, that is 10 by 6 ohms. Maximum value of current at resonance is source voltage by resistance. At resistance, inductor and capacitor get short circuited, so only resistor value will be present, 9 amperes. At upper half hour frequency, maximum at upper half hour frequency, the current will be maximum value by root 2, and we have took here maximum value at resonance, because at resonance condition only you will get the maximum current. That's why he took the maximum value at resonance. See, Inductor and capacitor are connected in series, and inductor having a Q factor of 60, it is connected in series with a capacitor having Q factor of 240. He is asking the overall Q factor. Same, it behaves as a capacitor which are in series. 1 by Q is equals to 1 by Q1 plus 1 by Q2. So same acts as capacitors. He is saying that inductor and capacitor are connected in series. This having the Q value 60 and this is having the Q2 value 240. So this both will act as a capacitor series connection, and calculations will be done as capacitor series connection. In this question, he has given the voltage across the circuit and current. In the voltage, DC term is 5 and 10 cos omega t plus 60 degrees. Current term is 5 plus x cos omega t. Omega value he is given. He is asking average power delivered to the circuit is 0. Then the value of x. He is asking to find the value of x. Average power is 0. He is saying. You can write this equation as 5 plus 10 cos omega t plus 60 minus 180. It can written as 5 plus 10 cos omega t minus 120 degrees. He is saying that average power is equals to 0. Average power is you can write average power as 5 into 5 plus cos terms 10 by root 2 into 10 by root 2 into cos 120 degrees, which is equals to 0. 25 plus 10x by 2 cos 120 is minus 1 by 2, which is equals to 0. If this goes right side, 10x by 4 is equals to 25. 5 5s are 25, 5 2s are 10, 2 2s are 4. X is equals to 10 ohms. 10, not ohms. 10 amperes. This question, he has given the RMS source voltage and internal impedance 1.2 j ohms, feeds a load of impedance 7 plus 4 j in the figure below. He is asking the reactive power consumed by the load. Here you can write I is equals to V by Z, where V is 20 at an angle of 0 by total Z is 8 plus 6j. You can write it as 2 at an angle of minus 36.86. Okay, he is asking reactive power consumed by load. I square I RMS square into x, which is equals to 2 square into 4, which is equals to 16 VAR, which is V. In the circuit shown below, sum of the two voltages V1 plus V2 is sin 2 pi omega R plus 1 sin 2 pi 30,000 R. The RMS value of current through the resistor will be minimum if the value of capacitor. So he is asking the RMS value of current through the resistor. Current through the resistor should be minimum, means impedance should be maximum. Here it is given that RMS value of current through the resistor is minimum. RMS value is minimum. That implies IRMS is equals to 0. Here second frequency is 3 times the first frequency. We know f is equals to 1 by 2 pi root LC. From this we can say that f is inversely proportional to root C. So f2 by f1 whole square is equals to C1 by C2. That implies C1 by C2 is equals to F2 is 9. So C2 is equals to C1 by 9, where C1 is 2.5. To make RMS current as 0, this must get open. This is open for V1 voltage and this is open for V2 voltage. So C2 is equals to, this is C1, this is C2. C2 is equals to 2.53 divided by 9, 0.28 microfarads. These two are the important statements which are asked in many competitive exams. The total instantaneous power supplied by three-phase AC supply source to a balanced RL load is constant. Total instantaneous power supplied by single-phase circuit AC supply varies sinusoidally with double the frequency. So single-phase supply varies and three-phase supply remains constant. Keep that in mind. This question comes under the topic of two-port network. In this, such connection is given. See, the I current flows in this and I current leaves this. See, this network and this network is almost same. So I am writing the Y parameters of this network. I will draw the Y parameter of this. I will draw the pi network. Here you will get 4 plus 1, 5, and here 2, and here 2. This is port 2 and this is port 1. But these are the impedances. You must convert them into admittances, that is 1 by 2, 1 by 5, and this is also 1 by 2. Now if you want to write the Y parameters, you can write, you must add these two, 1 by 2 plus 1 by 5, 0.5 plus 0.2, this is 0.7, and negative 0.2, and this also negative 0.2, and this is 0.7. This is of the first network. Second network is also same as the first network, so write same as it is. Say simply 4 and 1 are interchanged here, so write same values. Now these are in parallel connection. You must add the Y parameters, Y1 plus Y2. You will get 1.4 minus 0.4 minus 0.4, and this is also 1.4. In this question he is asking to find out H12. V1 is H11 I1 plus H12 I2. So H12 is V1 by I2, where I1 is equals to 0. Means this is V1 and this is V2. Here the current entering I1 is 0. Note it as VA, note it as VB. From this loop we can write V1 is equals to VA minus VB, where VA is V2 into opposite impedance by total impedance minus VB is V2 into opposite impedance by total impedance. You will get it as V2 into Z1 Z2 minus Z1 by Z1 plus Z2. Here I have done a small mistake. V1 is H12 into V2. This is V2 where I1 is equals to 0. From this we can write V1 by V2 is equals to Z2 minus Z1 by Z1 plus Z. In this, these both are in series and these both are in series. So option A is right. In series circuit shown in figure for series resonance, the value of K coupling coefficient at resonance inductance can be written as J2 plus J8 plus J2 omega m, which is equals to J12. Don't take negative value. You will get omega m. K is equals to m by root L1 L2, where multiply with omega in numerator and denominator. Omega m by omega L1 plus omega L2, which is 16. So here the main mistake you will do is you will take capacitance value as negative. Don't take it as negative, take it as positive. And here L1 plus L2 plus J2 omega m you have to take here. You have to multiply omega m with 2. In this question, he is asking to find the value of RMS line voltage for below circuit. If RMS line voltage is 100 ohms, will be. He is asking to find the RMS line voltage VL if RMS line voltage is 100 ohms. This is the three-phase AC source. You have 2 plus J3 ohms, 2 plus J3 ohms and 2 plus J3 ohms, and this is connected in delta connection, and these values are 9 plus J12. Now he had converted this delta 9 plus J12 into star. So Z star is equals to Z delta by 3, where Z delta is 9 plus J12. Z star will be 9 by 3 plus J12 by 3. You will get it as 3 plus J4. So 2 plus J3 with phase voltage, and when it is converted into star, 3 plus J4, and the voltage across the 3 plus J4 is 100 by root 3. Because it is a line voltage, we have to take the phase voltage. Phase voltage is equals to line voltage by root 3. So he has done the voltage division here. 100 by root 3 is equals to phase voltage into 3 plus J4 by 5 plus J7. You will is equals to 100 by root 3. From that you will get the phase value, and from phase value you have to calculate the line value. You know that line voltage leads phase voltage by 30 degrees. In LC circuit, there are 3 possible scenarios with source voltage. You multiply by sin omega t when initial voltage and final voltages are 0, and you will multiply with cos omega t when initial voltage is present and final voltage is 0. You will multiply with 1 minus cos omega t when final voltage is present. This is an important question. When two identical two-port networks connected in parallel, their individual transmission parameters are ABCD. Transmission parameters of ABCD of interconnected network will be A remains same and D remains same. That means diagonal elements remain same, and B element will become half and C element will become double. Note: if two networks are connected in cascade, the resultant may or may not be symmetrical. The resultant may or may not be symmetrical, but if two networks are connected in cascade, the resultant network will always be reciprocal. So it is always reciprocal when they are connected in cascade, but it may or may not be symmetrical in nature. In this question, he has given V1 in terms of V2. He is asking to find out ABCD parameters. In this network, first consider only this network. For second network, you will get Z parameters as 2 plus 1, 3, 1, 2, 1, 1. Now consider here only this network 2, 1, V2, V1, V2 and I1. This is sending I2. So I1 is equals to minus I2 plus V2. V1 is equals to, from this loop you can write 2I1 plus V2. Substitute this I1 value, you will get it as 3V2 minus 2I2. So V1 is equals to AV2 minus BI2. I1 is equals to CV2 minus DI2. From these equations you will get ABCD matrix as 3, 2, 1, 1. Now this network has ABCD parameters. It is cascaded with these parameters, so this both has to be multiplied. You will get like this. ABCD is multiplied with the second network, you will get the final value. Now shift this matrix to this side, you will get inverse. By finding the inverse, you will get the values as this much, and by multiplying these both matrices, you will get values as 7, 9, 3, 4.